Now, when I do this, I will post these notes. Hopefully I'll be able to save here in my iPad as a PDF and I'll post it. Nonetheless, there we go. Out of the way. Okay, so the book talks about set notation. There's different ways to present answers in this. So let's say we come up with x is less than or equal to 5, right? Let's say that is our answer. Now, when you see something like that, x is a variable, it could be any number. So when I look at this, I can just think about what values for x will make this inequality true. So less than means smaller, right? So I could plug in a 4 there, right? 4 is less than 5. 0, I could plug in -1. I can even plug in 5 there, and that's true. 5 is less than or equal to 5. The equal picks up the equality there, the trueness of the statement. In any case, when you look at something like this, you're going to have infinitely many answers. When you have infinitely many answers, you don't want to make a big list. In math, that would be kind of cumbersome. Let me go ahead and put in a scale. So here I just have a basic number line. You're probably familiar with this. This represents every number, every real number there is. Okay. Also, you could think of it as the x-axis of a graph. All right. And so in this particular case, I have to shade all the numbers that are less than or equal to 5. It would be helpful if my scale actually went to 5. I always like to go to one more than you need. In any case, I could start plugging in numbers, right? 3 works, 4 works, 2 works, 1 works, right? -1 works, 0 works. But those are whole numbers, right? There's a whole heck of a lot of numbers in between 3 and 4. So like 3.5 works, right? 2.4 works, and even 5 works, right? 4.1 works. So basically, if I want to present my answers, I'm going to have to shade all these numbers on a number line. All right, so these are all the values in green that satisfy this inequality. All right, and so that's the solution set presented graphically. All right, notice here I'm using a closed dot because 5 is actually included in the solution set. Now, it's really cumbersome, especially if you're trying to present your answer in a paper and you're writing. So there's a textual way of presenting infinitely many answers so you don't have to draw this picture if you're typing or something. And that's using interval notation. So in this particular case, we can translate this picture into the interval from -infinity to 5. And notice here I'm going to use a square bracket. The square bracket indicates the open dot. All right, so this is the graphical representation of the solution set. And this is the interval notation. That's a V. Okay. So 2 ways to present infinitely many solutions. And you'll see this a lot. It's sort of common. Let's look at another one. Let's say we had x is greater than -2. Let's say that was our answer. All right. And so if we were trying to present our answer, that was also going to have infinitely many solutions. All right, so now I'm looking at x as the variable, so I have to think about what will solve this inequality, right? What will make this true? About that. So I can just think in my head, 10 works, right? 10 is greater than -2. 4 works, right? 2 works, 0 works. -1 works, but notice -2 does not work. So at -2, what I'm going to do is do an open dot to indicate that I can get infinitely close to -2, but never actually include it. And then what I'm going to do is shade everything to the right, right? And so that's the answer here of all the numbers greater than -2 with the open dot. It's the graphical solution. In interval notation, what I'm going to do is use an open dot for the -2 and run that out to positive infinity. Okay, so also remember when you're on a number line, negative infinity is way over there and positive infinity is way over there. Also, with infinity, you always use the round parentheses for infinity, okay, because you can never actually include it. When you're including the endpoint, you use square bracket. When you're not including the endpoint, you use a round bracket, okay? So that's the basics of interval notation. Now from there, it just gets a little more advanced. Let's say we had x is less than 2. The mathematical keyword or x is greater than or equal to 4. So let's say this is our answer. Now that or in mathematics often means the union. Often, it always means the union. And the union, the notation for that is an upside down U. So you might see the keyword or in math, or you might see the symbol U. It looks like a U, it's not a U. It looks like, it's more like a horseshoe shape, but that means or. When you talk about unions, you're thinking about combining the results. Okay, so I'm going to put that in quotes. So we need to combine all the answers for x is less than 2 with all the answers for x is greater than or equal to 4. All right, so let's get a good scale. Let's go 0, 1, 2, 3, 4, 5. And now you want your tick marks to be equally spaced. All right, so you want a proper number line. And a proper number line like that, all your tick marks are definitely equally spaced. What I'm going to do first is look at this guy, all the values less than 2. So I'm going to put an open dot at 2 and shade everything less than. So all of these are solutions to this compound inequality, what it's called. And then I'm going to look at the second piece, which says x has to be greater than or equal to 4. So I'm going to put a closed dot there at 4, and I'm going to shade everything greater than, right? So that's the graphical representation of this particular solution set. Now we're going to want to convert that to interval notation. So we'll just do it piece by piece. For this left piece, I'm looking at negative infinity to 2 with a parentheses, right? For that open dot at 2. Union, square bracket, 2 to infinity, right? And you always use opens for those infinities. So that would be the interval notation interpretation for this particular solution, which is basically just a compound inequality. Let's do another one. I have here x is less than or equal to 7. And so now I'm using the mathematical use of the word and, or the logical use of the word and, I should say, greater than -1. All right, and so let's say this is our solution set. And we want to represent this, right? We want to represent this in interval notation, graphical notation. So let's create a number line. And is very different. So you got to be a little careful with and. And is in mathematics, the logical use of the word and, that means intersection. Means both of these conditions have to occur at the same time, simultaneously, right? And then the notation that goes with that is the upside down U. That means intersection. Okay, so to do these, it's a little tricky. It's a little different. So I'm going to do it in blue. Well, first let's get a scale. I need to get out to 7, so I'll start 0 over here. When you're making your number lines, always try to go like one more than you actually need. And again, you probably know this stuff. It's just preliminaries. We're getting like notation down first. We'll get to the meat of the subject later. In any case, I'm looking at, I did not mean to do that. So how do you undo? Perfect. So in blue here, I'm looking at this inequality, all the numbers less than or equal to 7. So what I'm going to do is I'm going to graph that sort of as a guide above the number line where I'm actually going to put the answer. Okay, so that's right there. All the numbers less than 7. Now I'm looking at this inequality. And what I want to do is plot all the numbers greater than -1. And at -1, I'm going to use an open dot. And so that's all of these numbers. Okay. Now for the final answer, the keyword and is the intersection. So you could see these two sets actually intersect here. And so what I'll do is I'll use the same open dot here on this side. And then over here, since both of these are closed in, I'm going to use a closed in dot at 7. And the intersection, or the and, is all of these x values, right? So all of these x values will solve this compound inequality simultaneously. Now, if I wanted to convert this to interval notation, all I have to do is say -1, non-inclusive, using a parentheses, to 7, inclusive, so using a square bracket, right? And so that would be the interval notation that goes with that particular compound inequality. All right, so that's the notation that we'll be using. And really quick, as an aside, you can actually combine ands. So you could say, like, this says the same thing. So you could say x is greater than -1 at the same time less than 7. So you can combine an and you could see it kind of reads like in between. When you see this, in between -1 and 7. So you can combine an and, but you cannot combine an or. If I tried to combine an or, look what would happen if I did. So here this says x is less than 2, which is also greater than 4. All right, and so when you look at that, hopefully I'll give you a minute to look at that. Hopefully you could see there's something terribly wrong with that. Okay, and what's wrong with it is that it says 4 is less than 2. And you're like, no, it's not. So that is false. Okay, so that's why you cannot combine an or, but you can combine an and. All right, so be a little careful there. That's kind of subtle. You do run into problems like that throughout class. Okay, yeah, so good. You'll watch it later. That's fine. All right, so that's what this is for. Don't feel bad for missing the lecture. Okay, the lectures are being recorded. This is a pure online class, so if you miss it, it's no big deal. You could watch it later. But I like to give the online classes a live feel. So hopefully you'll grow to like the videos. All right, so that's the basics in section 1.1. Now, what I am going to skip in 1.1 and let you do it yourself. Oh no, I was going to say the midpoint formula and the distance formula. Are those in 1.1? They might be. I don't know. So let's just keep going. So I'm in section 1.2. Well, you know what? I think the distance formula and the midpoint formula are actually in 1.1. I should have checked that out. How do you get the eraser? There we go. Let me eraser. If it's not, I'm going a little out of order. No big deal. Let's first look at the Cartesian coordinate system. René Descartes, 1800s. Right, so you have a Cartesian coordinate system, which is basically two number lines at right angles, right? And so usually you have an x-axis and you have a y-axis, right? And then you got some scale, 1, 2, 3, 4, right? Negative values are over here. And again, I know it's hard. It's hard for me here on the tablet. Try to keep your tick marks equally spaced. So notice I do have the graph paper, and that really helps sometimes. Right? And so any ordered pair, any point in the Cartesian coordinate system looks like x comma y, like an ordered pair, right? So for example, 2, 3 might be here. And then say -3, 3 might be over here. Yeah. Okay. And so in the Cartesian coordinate system, what you can do is connect two dots anywhere you're at. When you connect two dots, you can actually find the distance between 2 points. All right. And so that's your distance formula. The exams and the quizzes in this class is going to be open notes, so don't worry about memorizing it, even though you should memorize this. You should have memorized this already in maybe high school or something, right? So this is x1, y1, and let's call this guy x2, y2. All right, and so what you do for the distance formula is you take the difference in the x values, so x2 minus x1, square it, and then add that with the distance and the difference between the y values. So y2 minus y1 squared, right? And then once you make those calculations, you take the square root of the whole thing, right? And so for example, if I wanted to calculate the distance formula here, or the distance, I would say, okay, the distance is pretty simply 3 minus 3. That's not drawn to scale. 3. All right, I just threw myself all off. Look what I did here. I plotted 2, 2 when it was supposed to be 2, 3. So I don't know how I'm going to fix that. So I think I'm just going to put here 2, 2. So I've already messed up my first video. Awesome. Like I said, you are getting the live feel. All right, sorry about that. So 2, 2 to negative 3, 3, say. Terrible example. Anyways, you take the difference in the x values. So here's my x values. I have a 2 and a negative 3, right? So when I take the difference in the x values, I'm looking at 2 minus negative 3. And then I'm going to have to square that plus the difference in the y values. So 2 minus 3. Now, when you're doing these, you got to be a little careful. It's easy to mess up the sign. So negative 3 is really plus. So this is 2 plus 3 squared. And then 2 minus 3 squared. I'll do that next. So I'm just showing my work. Part of showing my work here. All right, so 2 plus 3 is 5. And then 2 minus 3 is negative 1. I'm sorry, I'm getting used to this Apple. It doesn't have palm rejection. The palm rejection on my PC was much better. So 25, negative 1 squared is 1. And so I get the square root of 26. All right, and so this distance is the square root of 26 units, whatever the units are. And that's using the distance formula. So it's basically just think of that as like a formula that you'll have to memorize and plug into. All right. Now, you can also get this midpoint right here with a formula, the midpoint. The midpoint is an actual ordered pair, so the midpoint's pretty simple. The midpoint is a formula. It's the average of the x values, comma, the average of the y values. Okay, and you can plug into that and actually get the midpoint, the point in between negative 3, 3 and 2, 2. All right, so I think that's section 1.1. Those are the highlights. That's about all you really need. Okay, now in 1.2, we start talking about functions. We start talking about relations and functions. Okay, so we got about 15 minutes here. I want to go a little quick. So just really quick, you don't have to memorize this. A relation is just any set of ordered pairs. And so with that simple definition, a graph, you know, so maybe something like a parabola, something like that, right? A parabola you might be familiar with, is a relation. Because you can think of it as just a big set of ordered pairs, right? All of these, this line represents just a bunch of dots, right? And so any ordered pair looks like x comma y on the Cartesian plane, right? And so by definition, that's a relation. Now in this class, we're going to be studying mostly special relations called functions. Functions are relations where each x value is unique. So a function is a relation where each x value is unique. Now, there's a number of ways to define a function. Our book has some sort of more technical definition, but this is a pretty simple definition. So you could see here for the parabola, that's a relation that's also a function, because each x value is going to have each point, right? Each ordered pair, as I look at this, each one of these dots, if you think about it, is going to have a different x value. Now let's compare that to, say, the graph of a circle. We will be graphing circles later. Okay, so let's say this is a circle where we have a radius of 1. And that's our unit circle. When we get to conic sections, we'll be graphing circles as well. All right, so think of a circle as an ordered pair. I mean, as a relation, because there's a bunch of ordered pairs, right? Each point on the circle is like a dot, right? And so just a big collection of ordered pairs, x comma y. All right, so a circle is a relation, but a circle is not a function, because I can see this point right here and this point right here. They're going to have the same x value. So it might be like 2/3, right, comma some sort of y value. This would be a negative y value, and this would be 2/3 comma positive y value. So you see two ordered pairs with the same x value. So this is not a function. Whereas this one is a function. Okay, so that's what that means. Now, there's a really simple test called the vertical line test. You can abbreviate that to VLT. So the vertical line test is a test to see if a graph or a relation is a function. Okay, so if any vertical line crosses twice, then it's not a function. Crosses the relation more than once, then it is not a function. All right, and so let's go back to the graphs here. And so you can see here, if I draw a vertical line anywhere on the parabola, it only crosses once, right? So it passes the VLT. But on a circle, if I draw a vertical line, see how it crosses it twice, right? So that fails the VLT. All right, so if it fails the vertical line test, it's not a function. If it passes the vertical line test, it is a function. All right, so that's kind of important, because we're going to be dealing with functions in this class. Now, with that definition, we have to define the domain and range. Okay, so the domain is simply all possible x values right? And the range is all possible y values. All right, all possible x values is domain, all possible y values is the range. So let me do a couple quick examples for you. And I think you probably already know this stuff. All right, and so let me give you a relation. Let's just make like a parabola, shift it up 1 unit. Sorry about the ugly graph here, but let's say that's at a 1. We have a 2, minus 1, minus 2, and then we got 1, 2 this way. All right, and so here we have a parabola, and you can think of this as like a relation. Just think of it as a big locus of points, a big set of ordered pairs, right? It is a relation, it is a function, it passes the VLT. All right, and so what we're going to want to do is find the domain. All right, so the domain is all the possible x values. And so this is my x-axis. Oh boy, I think I just zoomed in a weird way. How to get it back to 100% zoom, I do not know. Okay, so let's just say we have this parabola here and we want to calculate the domain. So just look at your graph, right? And just sort of project all of your x values down. And so I could see if I choose an x value of 2, I'll be able to find an ordered pair. If I choose an x value of 1, this has an x value of -1, this has an x value of -2. So you could see from the picture that any x value is possible on this graph. All right, and so the domain here is -infinity to infinity or all real numbers. So the fancy R is the same thing as that interval. Now, when I want to try to calculate the range is going to be all the possible y values. So look at your graph. What are the possible y values now? So you're looking this way. And so I could see 1 is the smallest y value, right? And then all of these numbers are going to be good y values for this particular graph. Now, -2 is not a good y value because there's no graph for that. Okay, the only possible y values here are going to be from 1 off to positive infinity. So when you have a number line that's kind of sideways, negative infinity lives down here, positive infinity lives up there, negative infinity is here, positive infinity is over there. All right, and so the domain is all real numbers, whereas the range is just those guys. Let's do, so this is a quick example. Let's do another example really quick. Let's look at, say, like a circle. All right, a circle is a relation, it's just not a function. So again, let's do the unit circle. So let's say that's a 1, this is a -1, and this is a -1 as well, right? We're on the Cartesian coordinate plane, so this is x, and this is y. All right, so thinking of a circle as a big locus of points, right? Just a bunch of ordered pairs, right? X comma y, just a bunch of points. That's all a circle is. They're just infinitely close together. So the domain are all the possible x values. So for this, the possible x values you could see here are between -1 and 1. Right, and so I can spell that out. I could say, all right, the domain here is from -1 to 1. Actually, they're inclusive, right? Put that back. Go back to blue. Since we're actually including the endpoints, I'm going to have to erase these and put square brackets, right? Those are inclusive. And the range, do that in red, those are the y values. So that's this part. Yeah. And so the range is going to be, again, from -1 to 1. Right? So the domain and range are kind of the same, but these are x values and these are y values. So they're not like really the same. Whew. Okay, so that was pretty quick. Domain and range, vertical line test, we got that. Awesome. Let's go into section 1.3. It's a little quick. We're going quick, right? So hopefully, honestly, hopefully this looks like review. So I don't feel like bad going quickly. But you can work on them slowly on your own time here. So function notation is going fast. Now, in the past in algebra, we were always looking at like y. Let's say we have a linear 2x plus 3. So that should look familiar, right, from your algebra class. Okay, and so that would be a linear equation. In this class, we're going to use function notation. As you move up in math, you got to start using different notations. And so instead of saying y, what we're going to do is say f of x, right? 2x plus 3. So these two things say the same or give the same information, right? And so I got to get used to the touch sensitive. When I push hard, it gets thicker. All right, so this and this, they're the same. The only difference is that f of x is getting replaced for y, and that's a theorem. F of x is just a placeholder for y. It's the y value. Now, the reason we use this kind of notation is because we plug in numbers a lot. And so this facilitates that operation, the operation of plugging in numbers. All right, and so that's what this notation is actually good for. So in the past, when I look at this one, the problems might have said, when x is 3, what is y, right? When x is 3, what is y? You'd plug in x is 3 and you'd figure out what y is. Well, we can do the same thing in higher level mathematics by saying f of 3. Okay, this says the same thing in notation. Okay, when x is 3, find y. And we don't have to actually write out a sentence. And that's important because we're going to be doing this a lot, right? And so to find f of 3, wherever you see an x, you're going to plug in 3. So that would be 2 times 3 plus 3, right? Which is 6 plus 3, or 9. Okay, so so here f of 3 actually equals 9. So what does that mean? In our old algebra way of thinking, that's 3 comma 9, right? That's the ordered pair, 3 comma 9, right? When x is 3, y is 9. All right, and so that's what function notation is good for. Let's do another example. You could plug in anything. So let's say, for example, it wanted f of -5. Okay, so if it wanted f of -5, we use our function, which is defined right here, 2 times x plus 3. And then so wherever we see an x, we're going to plug in -5, right? So we have -10 plus 3, which is -7. So f of -5 is -7. We might see something like this. For example, you might see f of 0. So in other words, what is y when x is 0? Well, we could do that, right? 2 times 0 plus 3 equals 3. And it might even say like fractions, right? So what is f of 1/2? Well, that would be 2 times 1/2 plus 3, which is 2 times 1/2 is 1. 1 plus 3 is 4. Yeah. Might say f of -0.1, right? And so 2 times -0.1 plus 3 is -0.2 plus 3, which is 2.8 or something. I don't know. Function notation facilitates plugging in points. That's why we have it. All right, we will be plugging in points a lot. Now, it does get a little confusing because the point that you plug in may not be the point that you plug in. It actually may not be a number. It might be a letter. So for example, let's say we let f of x equal some sort of quadratic like x squared plus 1. Yeah. And so this is our definition. It might say, for example, it might say to find f of 2. Okay, so if it says find f of 2, you just plug in 2 wherever you see an x. So that would be 2 squared plus 1, which is 5. But it might actually say find f of a. Okay, so it may not be a number. And so we're going to plug a variable a in wherever we see an x. So in this case, we're going to get a squared plus 1, right? Because wherever we see an x, we're plugging in a. And then that doesn't simplify any further. That would be as far as you can go. However, sometimes it does simplify further. So what if it wanted f of a plus 5, right? If it says f of a plus 5, again, wherever you see an x right here, that's where you're going to plug in a plus 5. And so since it's a binomial, I'm going to use parentheses squared plus 1 because that follows my template, right? And then inside there, I'm going to plug in a plus 5. All right, and then I have to FOIL that. So that's going to be a squared plus 10a plus 25 plus 1. So you can see here it does simplify. A squared plus 10a plus 26. All right, that's as far as I can go. And that would be a plus 5, f of a plus 5. Moral of the story, you're not always plugging in numbers, right? Sometimes you're plugging in functions into functions, and that throws people off sometimes. But that's the use of function notation. Okay, before we move on, let me just do one more because this really throws people off. So here's an example. Let's just do something linear. Let's say we have, yeah, our time is kind of up, but let's say we have here f of x equals, let's go with 3x minus 5. And it wants us to find f of x plus h. Now, this is going to be part of a quantity that's important later. But what this is saying is to plug in x plus h wherever you see an x. And I know that throws people off, like it's x, it's the same x, it's confused. Whoops, excuse me. It's confusing. So I'm looking at this as my template. So what I like to do is wherever I see an x, I'll put a parentheses first, and then I'll plug in whatever it wants me to plug in. So in this case, x plus h. After which you then do the math. So that 3 has to be distributed. I get 3x plus 3h minus 5. And that doesn't simplify. So that's as far as I can go with that. That would be f of x plus h. That's part of the difference quotient we're going to get to later. Okay, so that's our function notation. And there's a little more to it. Our hour is up. Maybe I'll make a little function arithmetic video later and I'll post it. But that should definitely get you started for today.